Okay, great. So hello everyone, and so today actually my idea is to cover some part of electrostatics where we can talk about electric force, etc. Okay, and I will more focus on some of the numerical problems today, and I'm not going to revise units and vector analysis as already in the last two lectures I did that. So the idea for electrostatics, before going to electrostatics, let's try to understand fundamental problem of electrodynamics. Okay, so the very first thing which people try to see, that if you have a source charges like this, you can see here. Okay, let me take the pointer. So these charges, let's suppose these are the source charges, and we wanted to have the effect of these charges to some charge, let's suppose capital Q, which we call it as a test charge, and we wanted to find that what are the effects Q will, the capital Q will feel in the field of these kind of source charges. So the idea was that, this in principle, the position of these charges along with the test charge could be a function of time, and they can have velocity, they can have acceleration, and all dependencies are there, and the interaction should be then calculated accordingly. Okay, so the idea basically with this came like, okay, let's apply the principle of superposition, and then try to see what force Q will, capital Q or the test charge will feel in terms of source charges. So principle of superposition generally says that the interaction between any two charges is completely unaffected by the presence of others. What that means? That means that if I wanted to have the effect of, let's suppose, some Q1 here, okay, over the Q, then we can just calculate the Coulomb force between Q1 and Q without saying that what are the effects which Q1 and Q2 or Q1 or Q3 or Q1 or Qi is going to feel among each other. And then just add everything like a vector, because force is a vector quantity, so you can add it and you can say that this is the principle of superposition that we try to find. However, this is only true if it is obeying the principle of the Coulombs law. So what that means, let me write it here, and then I will move forward about this very important point that one has to understand. So that Coulomb force generally is something like F is given by, let's suppose you have a Q1 and you have a Q, so divided by R square, which is the distance between Q1 and Q, and then there will be a direction. So let's suppose that direction is given by R, okay, something like this. And obviously there will be, if you use in SI units, then you have to have 1 over 4 pi epsilon naught. Okay, so these are the simple thing that we know. But now principle of superposition says that if one charge Q1 has this force over this test charge, then we can add these whole forces similarly with F2, F3, F4, like that. And then the principle of superposition says that total force will be sum of all those forces, and it should be a vector sum. Okay, so that means you have F equal to F1 vector plus F2 vector and so on. Okay, so this is the principle of superposition. So it looks like that this is very very simple and very obvious, but I put it a star here in case to understand that why it seems to be very obvious. However, it is not so obvious in case, as we know, that Coulomb force says that this force is proportional to the product of two charges. Okay, but if let's suppose I say that this force is basically depend on sum of the charges. Okay, so and sum of the total charges and square it, something like that. That means, let's suppose if some law says that F is proportional to sum of all charges square. Okay, let's suppose we have two charges and we say that this is nothing but the square of this. Okay, then the principle of superposition like this is not going to be hold. And the reason is very simple, because you see, if you expand this Q1 plus Q2 whole square, then it is going to give you a interference term. That means this is something like A plus B whole square. So you have Q1 square plus Q2 square plus 2Q1 Q2. Okay, so then you cannot write simply the superposition principle, which states that you have to just add that you have to have just a vectorial sum of all the forces between the source charges and the test charges. Okay, so this cross term is basically very important to understand that the principle which we are talking about in the Coulombs law is the experimental fact, and superposition is not a logical necessity. Okay, so try to understand this point, and that's why I wrote the whole statement here, which one needs to read and digest. Okay, because in competition, in competitive examination or in some kind of high level of interview, you might get such kind of questions, which could be very important, when you give the answer. So let me just read it out, and if you have any doubt, I mean, you can ask the question. So what it says that the principle of superposition may seem obvious to you, but it did not have to be so simple. So if the electromagnetic force were proportional to the square of the total source charge, which I just showed here, for instance, the principle of superposition would not hold, since Q1 plus Q square, Q1 plus Q2 whole square should not be equal to Q1 square plus Q2 square. Why? Because there is a cross term, right? This is 2 times Q1 Q2. Okay, so therefore the superposition principle, which we are talking in terms of electric field or electric force, are the experimental fact which we are using here. Okay, and I hope now this statement is very clear, that principle of superposition says that the interaction between any two charges is completely unaffected by the presence of the others. So this is the experimental fact which we are basically using as a principle of superposition. So anyone has any confusion or any question on that note?
Sir,
Yes.
Cross terms cannot be added, or
No,
why
it could
we
be added.
neglect
You
cross
see,
terms?
yeah, it could be added, but the addition is now the product of two charges, not the square of these two charges. You understand? So your principle says that this is something like this. So this force is like that. Okay, but what about these two terms? You understand? The dimension is same. Dimension is the you have a Coulomb square. Okay, but this cross term will not allow to add something like this. Okay, and
Okay,
when you do these terms, by writing itself, you will find that this is not going to hold. Okay, so it is not very obvious. Good.
okay,
All
sir.
right. So with this introduction, let me start the definition, proper definitions of Coulombs law, etc., which we which we already know. And I will try to today, focus on some of the numerical problems and definition of electric field, etc. Okay, so let's begin with something called electrostatics, where source charges are stationary, though the test charge may be moving. Okay, so as I said before, that in principle, electrodynamics include that your test charge as well as source charges can have some movements. They can have a velocity. Their positions are basically the function of time. Okay, and these things we're going to learn later on, where we talk about how electric fields are moving within a charge current, and then calculate the magnetic field, etc. And also a special theory of relativity is going to be included there. There are many other things. Okay, but for the timing, we are trying to just focus on electrostatics. And once, so this is also very important point which I mentioned here, that in electrostatics, your source charges should be stationary. However, test charge may be moving. So if you go back to the slides back, so these are the source charges and these are the test charges. That means we wanted to find effect of this charge to somewhere else on some charge. Okay, so these are the test charges and these are the source charges. So always try to distinguish. When I'm saying source charges, you understand that we wanted to calculate the effect of this source charges to some test charge. Okay, good. So this is the definition of electrostatics. One has to be very clear on that, because one could say that in case a test charge can have some movement or not. So, but they could have a movement. They can be static. They can also move. Okay, the source charges should be stationary. Then we define it as a electrostatics. Okay, so very first thing, Coulombs law. We know that if there is a source charge Q, we wanted to put some test charge capital Q, which having the distance like r, and r was defined, if you remember, in terms of the position coordinates. So if you define with respect to the position of Q to be some r and position of capital Q to be some r prime, then it could be just a vector sum of these two position vectors. So it says that force is a vectorial quantity, and this is given by 1/4 pi epsilon naught, the product of these two charges, which is Q times capital Q divided by r square, and r cap is the unit vector in the direction of this r. Okay, and epsilon naught, we know that this is when we say this is epsilon 0 or epsilon naught, this means this is the permittivity of free space, and it is given as 8.85 times 10 to the power minus 12. And in the SI unit, we can always represent in terms of Coulomb square divided by Newton meter square, which is very easy to calculate. What you have to do, you have to just, because this 4 pi is just a constant. So if you put epsilon naught here, and then force is going to be in the denominator here, and then you can see that this is charge. So this is Coulomb square, and force is coming here. So Newton times, and this is the distance square. So this is meter square. You can calculate by the visibility itself that what could be the unit for such constants when we talk about Okay, so and r, as I said before, that this is just like a vector sum. Of the position vectors of both the charges. So this is r minus r prime, where this because this is not bold, so this is normal font. So you have this as a magnitude, and r cap is its direction. So this is the Coulombs law, which we know from our previous classes as well. Okay. So now let's suppose we have a 12 equal charges, okay, Q, which are situated at the corners of a regular 12-sided polygon. For instance, let's say these are sitting on the numeral of a clock face. Okay, so what should be the net force on a test charge Q at the center? Can anybody just give me an idea? So this is a very simple problem. What is happening here? That let's suppose you have something like a clock. Okay, so you have 12 divisions. So it's 12, 6. You have a 3 here, and then you have a 9 here. Then obviously 1, 2, 4, 5, 7, 8, 10, 11. Okay, so this test charges, the 12 equal charges of Q are sitting here. Okay, so this is also Q, here also you have Q, and etc. Okay, now we wanted to calculate the net force on test charge Q, which is sitting in the center. So what could be the net force? Anybody can have answer? This is very quick question. Yeah, I mean, this kind of questions can be solvable in a second actually. So you have to apply. What do you have to apply? You have to apply a
Superposition.
Yes, and then what is going to happen here? So let's suppose, yeah.
Sir, we have to add it, the 11 force, which is imparted by the charge Q.
Right. So, and what could be that in total? In this situation? So what is going to happen? Let's say this Q, we wanted to find according to this force law, if we calculate this force. So the direction of this force is going to be like this. And the distance is obviously, let's suppose this is R or something like that. And from everywhere, we have the distance R from Q to Q. And one of the Q is sitting here as well, okay, at 6. So this force is going to be equal and opposite in direction, right? You agree with that?
Yes, sir. Sir, I think then the net force will be 0.
0, right. So this is the very interesting question that you can just solve like by saying things, you know. So similarly, what is going to happen? So the opposite charges, which is sitting here, for example, at 3 and 9, they are going to also cancel out because the distance distance are same and the directions are just opposite. So for this is also true for you know, this situation here, and this is true for all the 12 positions. Okay, so the net force is going to be 0 clearly. Okay, now let's do one experiment. Okay, and suppose one of the 12 Qs is removed, the one at 6 o'clock. Okay, so what is the force of Q on Q? Explain your reasoning carefully. Okay, so what could be the answer here? Let's suppose I removed this one at 6, so there is no charge here. Okay, and now we have only 11 Qs left out from here to here. So what could be the force on Q then?
Then, sir, force will be due to a single charge.
And that should be?
That should be equal to sir, Coulomb force.
Yeah, it is just like this expression you expect, right? So, okay, probably I didn't write that term here, but yeah, so you can hope that if these quantities are given, then you can calculate simply, you know, the Coulombs law, which is providing for one charge accordingly, because every other charge is going to cancel out, but this charge is going to not cancel out by any component. Okay, very good. Okay, so then after, so these are the reasonings that you can give behind this sort of problem. Now let's suppose we have this situation where you have 13 equal charges Q are places at the corners of a regular 13-sided polygon. Now, what is the force on test charge Q at the center? And if one of the 13 Qs is removed, what is the force on Q? Explaining your reason. Okay, so let me just give this as a homework so that I can move towards the other thing. And in the next lecture, please give me this answer. Okay, with a proper reasoning. Okay. Yeah. So let me move towards the definition of electric field. And for that, again, we have to have something like this. So you have a XYZ coordinate in the right-handed system. And this source charge have some position vector, let's suppose Ri prime, and your field point is from the origin have a position vector R. So you know that this is Ri, which is our general notations which we use. Now we wanted to find electric field at point P. So there is, now you see, this is a field point, this is not a test charge. So from the previous slides, we saw that we always put a test charge here, but now there is no test charge. I just wanted to calculate what could be the field strength at some point P. And this point could be anything like here, 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 wherever I wanted to just calculate. So to do that, what we can use, because we know that the superposition principle tells us that we can add all the forces vectorially at some point. Let's suppose there is a test charge here. It is now just like a supposition. Okay. And then we have to use the superposition principle. And according to that, since 1 over 4 pi epsilon naught is the constant, so this constant is going to be, sorry about that, going to be out. And then you can write this is as Q1 Q over R1 square, R1 unit vector plus Q2 Q divided by R2 square, R2 blah, blah, blah. Okay. And then since this test charge is also constant, this is appearing in each term, so we can also take it out. And then we can say that Q over 4 pi epsilon naught is this. And then we can simply write it as a Q1 R1 square, R1 blah, blah, blah. Okay. So from here, we can define a quantity which we call an electric field, where electric field is given by the terms which is shown here in the bracket. Okay. And this Q is simply like that. And you know that 1 over 4 pi epsilon naught can be taken with these terms. Okay. So F is going to be equal to your test charge times the electric field E, where electric field is a function of R. This is very important here to note that this is a function of R, and this is given as 1 over 4 pi epsilon naught summation of all those terms. So we can write this whole term in terms of the summation. Okay, so this is just a notation which you know from your various classes. Okay, so this is going from I equal to 1 to n, and when you substitute this, you will just getting the same thing which is denoted here. Okay, so important thing to understand here that electric field is the function of the R, which is the is the position vector. Okay, and this position vector is basically, so let's suppose you wanted to calculate electric field of any charged particle. Let's suppose we have an electric field here, and we wanted to calculate electric field at this point. So this is also dependent on distance and obviously the position vectors, whatever. But I wanted to calculate here, then this is going to be different than what we have here. Okay, so that's why this is a function of R, which is very important here. So by definition, everything is clear here. And obviously I wrote it here. So E is called the electric field of the source charges. Now, to complete the definition, what we can say that the electric field is a vectorial quantity that varies from point to point and is determined by the configuration of the source charges. Physically, ER is the force per unit charge, which you can say from here. So if I wanted to write from this expression, what we can write that electric field is a vectorial quantity. So you can denote it as a vector, is nothing but force per unit charge, okay, divided by Q. Okay, so this completes the definition of electric field, which you learned. So I just give you a short overview that what is electric field, what are the electric forces, how superposition principle acts. Now let's move towards the one of the problem and try to understand that how basically practically we're going to calculate electric fields. Okay. So, but before that, I mean, are there any question on electric field or is it clear? If you have any question, please interrupt me while switching on your mics. Okay. So let's take one example and try to calculate the electric field at a distance z above the midpoint between two equal charges q, a distance d apart. Okay. So these two charges are there. Okay. In this question, it is given that these are the two charges, and the distance between these two charges is small d. Okay, and charges are q and q. We wanted to find electric field at a distance z above the midpoint between two equal charges. So this is the midpoint. So if I choose this midpoint, it means the distance from this q to this q is d by 2, and also from this point to this q is d over 2. And let's suppose this is lying in the x direction, and we wanted to find this electric field at point P, which is at distance z from this midpoint. Okay, and let's suppose this is the z-axis according to our convention. Okay, so the very first thing is that what we have to do, we have to find, as we did in the previous definition, that we wanted to find the electric field due to this charge at this point, and this is going to be like something like this. Okay, and similarly, one could have the effect of this q at this state point, which we can calculate simply like this. Okay, but now the situation is that these are not along the axes, the choice of axes which we have chosen. Okay, so what we can do then, we can just assume that, let's suppose that this is angle theta. Okay, and then we choose our this x and z coordinate, and accordingly we take the components. Okay, so first of all, let's do this for this charge. Okay, let's suppose this charge is 1. So due to this charge, let's suppose the electric field is given as E1. Okay, and when we resolve towards the x-axis, so according to our convention, what could be this? So this angle is theta. Okay, I use this angle as a theta. So it means this angle is also going to be theta, and hence this is going to be 90 minus theta. Therefore, the component of E1 towards x-axis is going to be E1 sine theta, right? I hope there is no doubt due to this. And the z towards the z-axis, this should be E1 cos theta. Is it clear to everyone? Similarly, let's suppose this is 2. So for 2, again, we can have this as a, let's suppose this is E2. However, since we know that the charge is same, which is Q here, so we can also take, due to this to charge 2, the electric field is simply E1. Okay, or in your convention, you can generally take E simply. And then again, do the components here. So this is going to be E1 sine theta. Okay. And similarly, in the z-axis, you're going to have a E1 cos theta. So what that means, you can see here that in the horizontal direction, your components are basically, because these are the vectorial quantities, so you can see that they are opposite. It means the horizontal component is going to sum up as a 0. However, the vertical component is going to be add up, and you only left with the electric field in the z direction due to these two charges. So if I draw this, that means you have to have only electric charge, something like this. Okay. So up to this point, do you have any problem or any question?
No, sir.
Very good. So this is very clear, and see, I'm doing this step by step so that, whenever you solve a problem, don't try to remember, just do it by the whole procedure, which, we need to follow here. Okay. So how to calculate this capital E now, because now we know that this capital E is nothing but sum of these two. That means it is going to be 2 times E1 cos theta. And we know from our previous definition that this is along the EZ axis. So let's suppose this, I say EZ should be equal to 2 times 1 over 4 pi epsilon naught Q over R square cos theta. Okay, where R is the magnitude of this distance. Okay. So this expression is clear, or is there any confusion here? You
No,
agree
sir.
with this?
No, sir. Yes, sir.
Okay, that's good. So now what we can do, since the given quantities, now the point is that the question doesn't end here. Okay, because the given quantities is only Z, okay, Q, and distance T. So what we need to do, we need to basically represent, because we know here that this R is our assumption, and cos theta we don't know, I mean, because this is not given. Okay, so we have to basically find this cos theta and R, so that in terms of Z and T. Okay, which is very easy now, because you see this is a right angle triangle, and this base is Z, and this is T over 2, and R is nothing but this is a hypotenuse. Okay, so you can calculate cos theta like Z over R, and R as by using the right angle triangle formula, you can say that this is square root of Z square plus D over 2 whole square. Okay, so let's do this. So R is going to give you root over Z square plus D over 2 whole square, and then cos theta is given as Z over R, and then you need to just substitute this, and this is going to give you this expression. Okay, so this is the full understanding of a form, I mean, how to use the electric field formula to solve such kind of problems. We will get it more complicated one by one, but I'm just going through the basics. Once we get handy of this sort of things, then I will make it more complicated accordingly. Okay, but this is the way one should make any numerical problem. So now let's check that what physics basically we're going to learn from here. Okay, so when you want to learn some kind of physics like this, then one has to assume some of the criteria. So here we're going to assume that when Z is very, very large compared to D, then what is going to happen? Can any one of you can answer this question?
Sir, we can neglect D.
Right. So the moment we neglect D, that means it is just like a 0, and therefore it is going to be 1 over 4 pi epsilon naught 2 qz divided by z cube, and then this proportionality of z is gone, and then you will remain with the the electric field definition, which is which is simply the electric field definition which we learned before, due to the sum of the two charges. Yeah. Okay. So this is very interesting physics. You can see that you have a two charge. Okay. But if you see it a very large distance, it will appear. So it is just like something like you have a charge here with a strength to Q, and you are measuring electric field at some point here. Okay. So it is simply like this. So because these distances are going to be neglected at very large distance of Z. Okay. So these are very interesting examples. One should follow up with the concept of electric field. Next. Now let's suppose that we have a charge. In the previous case, we have a plus Q and plus Q, but now we have a charge, a plus Q and minus Q. Okay, so how this is going to be affected? Can anybody guess simply? That the situation is, yes.
They will attract each other.
Yeah, so and what could be the electric field then? At some point P. I mean, obviously they will attract, but at some point P, we wanted to calculate the electric field, because now this is, let's suppose I'm drawing here. So this is minus Q, let's suppose. Any quick observation?
Sir, electric field for both the charges will cancel out each other.
Can you repeat, because your sound broken up?
Sir, electric field by the both two charges will cancel out each other.
Which direction? I mean, here we saw that the horizontal component was 0, but the vertical component added. But in this situation, will be the same?
Sir, I think two electric field will be added.
Yeah, but which component?
E1 plus E2. Sir, particle component.
Are you sure?
Yes, sir.
Yeah, so you say now, the point is that for Q plus Q, obviously the direction is in this direction, okay? But once you have a minus Q, the direction is going to be changed, no? This is not more than like E2, like the direction which we had earlier. And then when you add these components, what is going to happen? The vertical components are going to be cancelled, and only you left with the horizontal component. No? Is it clear? So this is very important to understand, that what could be the directions, because now this is minus Q. So the direction is going to be towards the minus Q, and therefore now the vertical components are going to be cancelled out, and you left with only horizontal components. Okay, so here we added 2 e cos theta, but this 2 e cos theta is going to, in this case, is going to be e cos theta minus e cos theta. So these are going to be cancelled, but here we are going to have now the horizontal component in this direction, in the positive x direction, and we're going to receive it as a sine theta component. Okay, is the concept clear now?
Yes, sir.
Very good. So let's solve this problem quickly. So this is going to happen like this. So you have a Q minus Q. Now the other components, the vertical components are going to be cancelled out, and then you have the horizontal component to be added. And therefore, you can simply write this. So somehow, you know, when I do this mathematical formula, this should be R. Okay. So you have E equal to 1 over 4 pi epsilon naught 2 times Q over R square sine theta X. Now you see the direction is X. So this is these are the very important things that one should you know, notify when calculate things like this. So again, we have to represent this in terms of D and Z, because these are the two things which has been given to us. And this give you a very nice concept of something called dipole. And later on, we're going to see about dipole moment, which you might have learned, if you remember, in your class 12 also, about the, you know, dipoles, how to find the electric field due to the dipole, etc. So once you, you know, I mean, it is very easy to calculate. Once you put sine theta, then you're going to get some expression like earlier it was Z by R. Now it will be like D over 2 divided by Z, right? Because this is a perpendicular and this is the base. So your sine theta will be, yeah. So D over 2 divided by, so let me write it somewhere so that there should be no confusion later on. So sine theta should be equal to, because this is D over 2, okay. So, and you know that sine theta is given as perpendicular divided by R. So this could be D over 2 divided by R. And hence, you see that the moment we substitute the sine theta and the value of R by using the Pythagoras theorem, you're going to get Z square plus D over 2 whole square, 3 over 2. And this 2 is going to be cancelled. So now this is cancelled by this term, okay. In the earlier case, what we had seen, that this 2 remains, okay, because there is no involvement of this D over 2, rather than it was just involved this component and this component, okay. So therefore, we didn't have this 2 factor here. And now the situation is going to be again verified in case we have, oh my God, I think I forgot to write, or what happens? No. So yeah, so let's suppose now, actually, probably I missed something which I wanted to write here. So in this case, what is going to happen if again we say that Z is, you know, Z is very high comparing to D. So in this situation, what is going to happen? You can analyze these things by yourself, and you know, you will find a very nice concept of dipole, which we're going to use in one of the lecture set again. Okay, and if you have any confusion, obviously in the next lecture, I will try to explain it again accordingly. Okay, so these are some of the, you know, small thing as a homework. I left it so that you can also, you know, work out in home and come back to me with questions. Okay, so I will stop here, but let me just introduce one thing which we're going to discuss in the next lecture set, which is continuous charge distribution. So let's suppose you have some, you know, distribution of charge, and that could be in the 3 dimension as well, in 2 dimension as well as in 1 dimension. So you have some, let's suppose infinitesimal charge element dq, and you wanted to find electric field at some distance r at point P. Okay, so there could be three cases where you can represent this as a line charge. So you have a line charge, okay? So we can take an element of this line charge to be dl prime, and then we can denote it in terms of lambda. Similarly, we can take the surface charge and we're going to denote it as a sigma, which is in the 2D plane. Okay, and this is just the area, the infinitesimal area we are talking about, and due to this, what could be the field at point P. And similarly, we can take the volume charge rho if we have a three-dimensional object, and where we're going to denote it just like by d tau prime or something like this. Okay, so in the next lecture, I will do this, and the problem set is going to be more and more complicated. But you know, I will try to do my best to give you some understanding of this. And let's stop today's lecture here. Yeah, because I don't have, you know, according to the time I have to finish it. So, but yeah, before that, if you have any question, you can always welcome to ask. Anything? So if not, so then let me end the session today by thanking all of you who joined here. And